I want you to take a second and just look at the nearest pair of headphones you have lying around. Or, maybe the little metal box on your desk that you plug them into.
Right, like an audio interface or a headphone amp.
Yeah, exactly. We interact with these things every single day, right? You plug them in, you hit play, and you just expect this pristine, beautiful audio to instantly wash over your ears.
You take it completely for granted.
Totally for granted. But today, we are going to look under the hood. We're going to pry open that metal box and look at the microscopic obsessive battles that have to be fought at the level of electrons, just to give you that clean sound.
And it really is a battlefield in the truest sense of the word. I mean, when you sit down and look at what it actually takes to get digital audio out of a computer, translate it into analog voltage, and push it into human ears.
Without completely destroying it in the process.
Exactly. Without destroying it, you realize it is a minor miracle it works as well as it does. We are dealing with laws of physics that are just inherently hostile to delicate audio signals.
Okay, let's unpack this. Our source material for this deep dive is, well, it's a really fascinating window into that exact battlefield. We are looking at a master's thesis from 2013.
Which is pretty old in tech years.
Right. It was written by a student named Sylwester Komanek at the Wrocław University of Technology in Poland. And you might wonder, why are we tearing through a university paper from 2013 today?
Yeah, why bring this up now?
Well, it was recently translated into English and published for the wider world in 2025. And it just perfectly captures the artisan craft of building custom audio hardware. The thesis is a start-to-finish guide on designing a high-end digital-to-analog converter, or DAC.
The timeline is what makes this document such a compelling study, honestly. Because, in the tech sector, a decade is basically an eternity.
Oh, yeah. Phones from 2013 belong in a museum.
Right. Software evolves, processors become obsolete. But this project uses core building blocks, like specific integrated circuits, like the PCM1792 DAC chip.
And the SRC4193 resampler.
Exactly, and the TPA6120 headphone amplifier. These chips have completely stood the test of time. They are still prized by the most discerning audio enthusiasts today.
Which is wild to think about.
It is. It proves that low-level hardware design, specifically analog audio engineering, just operates on a completely different evolutionary timeline than standard consumer tech.
So our mission today is to unpack that timeline and the sheer human passion required to embark on a project like this. We aren't just going to read an engineering schematic to you.
That would be pretty dry.
Super dry. No, we are going on a journey into obsessive craftsmanship. We want to explore the blood, sweat, and the really profound dilemmas that go into hardware design.
And we'll decode the magic of these circuits using tangible analogies so you don't need an engineering degree to follow along.
Right. But by the end of this deep dive, you are going to understand the physics of your audio gear on a completely different level.
Because at its core, this project isn't just about music. It's a universal engineering challenge. It's the story of taking something incredibly fragile.
Like the math of an acoustic wave.
Yes, the mathematical representation of a wave, and defending it against a highly aggressive physical environment full of, well, electromagnetic chaos.
I love the human origin story behind this specific piece of hardware, too. Komanek was aiming to build this premium audiophile-grade device that could go toe-to-toe with equipment costing thousands of dollars.
So he was a university student.
Right, operating on a strict student budget. So to get these legendary, highly expensive Texas Instruments chips, he used this brilliant workaround.
The free samples program?
Yeah. He took advantage of a program where manufacturers offer free samples to engineers for prototyping. He literally just asked Texas Instruments for the parts, and they sent them.
It's a phenomenal hack. It allowed him to secure best-in-class silicon without, going bankrupt.
It speaks to such a deep resourcefulness, but it also highlights a critical reality in hardware design, right?
Oh, absolutely. Simply having access to expensive components does not guarantee a high-fidelity result.
It's not just plug and play.
Not at all. The artistry and the agonizing difficulty lies in how you connect those chips, how you deliver power to them, and how you shield them from interference.
Like the cardboard, the car isn't going to perform.
That is a perfect way to put it.
But I want to linger on your point about the timeline because it frames everything we're about to discuss. We live in a world where tech moves at blinding speed.
Moore's Law and all that.
Right. Transistors doubling every 2 years. We expect everything to be radically faster year after year. So if tech evolves so fast, Why are we still revering audio chips designed in the early 2010s? Haven't we essentially, solved audio by now?
Well, that assumption makes sense if you view audio through the lens of pure data processing. But audio technology is ultimately tethered to analog physics and human biology.
Okay, what do you mean by that?
Well, a smartphone becomes obsolete because the software it runs becomes infinitely more complex. It requires more processing power. Audio, on the other hand, is a solved problem mathematically.
Because standard CD quality audio is just translating, what, 44,100 samples per second?
Exactly. A chip from 2013 can process that math just as easily as a chip from 2025.
Right, because the end goal hasn't changed. We haven't evolved new ears that suddenly hear frequencies up to 100 kilohertz.
Right, exactly.
Yeah.
The target, creating a perfect analog voltage wave that drives a physical headphone speaker, is exactly the same today as it was 20 years ago.
And that is the crux of it. Solving audio isn't about writing newer, faster algorithms. It is entirely about fighting an invisible, unyielding physical enemy that is baked into the very nature of electricity.
Which brings us to the absolute nightmare of every single analog engineer.
Electronic noise.
Yes, we're going to spend a lot of time defining this because it is the central antagonist of this entire thesis.
His primary hurdle, like the entire stated goal of the project, was to design a circuit with an incredibly low noise floor. He was aiming for a maximum of negative 120 dB THD plus N.
THD plus N stands for total harmonic distortion plus noise, and achieving negative 120 decibels is an extreme, punishing level of clarity.
Just to put that in perspective for you listening, a standard consumer audio device might sit around, what, neglige 80 or neglige 90 decibels?
Yeah, around there. So pushing that down to negative 120 requires a fanatical devotion to clean circuit design.
Let's be very specific about what we mean by electronic noise, because when you hear the word noise, you might think of a truck driving by outside your window.
Or the hum of an air conditioner.
Right. But in the context of a printed circuit board, noise is something entirely different.
We are talking about microscopic electrical disturbances. We're talking about the random, chaotic movement of electrons inside the conductive materials themselves.
Yes, thermal noise, also known as Johnson-Nyquist noise. This is one of the most fascinating concepts in electronics to me.
It's wild when you really think about it.
It is. Any conductor that has a temperature above absolute zero, which is literally every conductor on Earth, has electrons inside it that are vibrating due to thermal energy.
And as they vibrate, they create these tiny random fluctuations in voltage.
So wait, even if the device is perfectly isolated and not even doing anything, the sheer fact that the metal is warm means it's generating microscopic electrical static.
Exactly. It's a fundamental law of thermodynamics. You cannot escape it. You can only minimize its impact. And thermal noise is just one part of the equation.
Right. You also have power supply noise.
Yeah. When a sound card pulls electricity from a computer or a wall outlet, that power isn't a perfectly flat, clean line of voltage. It is incredibly dirty.
It's full of spikes and ripples.
Right, and high-frequency garbage from other appliances on the power grid.
And if these microscopic ripples and thermal vibrations aren't ruthlessly controlled, they manifest in your headphones.
You might hear it as a faint, static hiss when no music is playing.
Or, even more insidiously, you might not hear it as a distinct sound at all, but it'll muddy the crisp details of a track. It smears the transients, right? Like the sharp strike of a snare drum.
Or the pluck of an acoustic guitar string. A high-noise floor is the difference between feeling like you are standing in the room with the musicians versus feeling like you are listening to them play from the other side of a thick, heavy curtain.
Which perfectly brings us to the core dilemma of the thesis. The optimization challenge. If you are an engineer tasked with hitting that negative 120 dB target, your first instinct might be to just brute force the problem.
Oh, sure. You could theoretically source the absolute most expensive aerospace-grade ultra-low noise components for every single millimeter of the board.
You could use resistors that cost $5 each instead of a fraction of a cent.
But if you do that, your sound card ends up costing the same as a used car, and it becomes completely unmarketable.
True engineering is never just about achieving the best theoretical performance in a vacuum. It is about finding the perfect equilibrium between performance and real-world cost constraints.
It's exactly. Kamenek wanted to identify the critical junctures where expensive platinum-grade parts were absolutely necessary and discover where he could deploy standard, inexpensive components without compromising the audio signal.
And it requires tracing the entire path of the audio signal and understanding the vulnerabilities at each stage. Let's visualize how vulnerable that signal is for a second.
Okay, let's do it.
Imagine you're trying to create a perfectly pure environment. Think of the analog audio signal as a large, beautiful glass of crystal clear mountain water.
I like this.
Right. So you have spent a significant portion of your budget on a high-end DF chip. That is your pure water source. But as that water flows through the circuit board, it has to pass through various filters and amplifiers.
And if you use even one single cheap resistor with bad thermal noise parameters in a critical part of that signal path,
It is identical to dropping a single drop of dark black ink into that clear water.
the drop of ink diffuses immediately, and the entire glass becomes cloudy. The pristine quality of the water is irreversibly ruined.
Because of amplification, right?
Yes, exactly. If a bad resistor introduces a microscopic amount of thermal noise early in the analog chain, that noise gets mixed with the music signal.
And when that signal hits an amplifier later on, the amplifier doesn't know the difference between the music and the noise.
It just amplifies both indiscriminately.
The ink poisons the entire downstream system. You've essentially wasted the potential of all those premium free sample Texas Instruments chips because you cheaped out on a part that cost 2 cents.
The noise floor of an entire audio system is ruthlessly dictated by its weakest link.
Which is why building a custom sound card is such an intricate, paranoid puzzle. You are constantly anticipating where the next drop of ink might fall.
And building elaborate physical and electronic defenses around the signal path.
So if the audio signal is this vulnerable, how does an engineer actually build this fortress? Let's walk through Commonec's architecture, starting right at the gates.
We have to look at exactly where the digital signal first enters the device.
Right. In this project, there are 2 main entry points. You have a USB connection from a computer and an optical input called toe-slink.
And the defenses deployed at these 2 gates are fundamentally different, but equally brilliant.
Let's examine the USB input first, because that's the most common way people interface with external audio gear today.
From an electrical engineering standpoint, a standard computer is arguably one of the most hostile, noisy environments imaginable for delicate analog audio.
Oh, modern computer motherboard is an absolute war zone of electromagnetic chaos.
Truly.
You have a CPU switching states billions of times a second, drawing massive, sudden spikes of current. You have a graphics card pushing hundreds of watts, fans spinning, creating electromotive force.
And all of this activity dumps a tremendous amount of electrical noise directly onto the computer's ground line.
And standard USB cables carry a ground wire. So if you run a regular USB cable from that chaotic computer directly into a sensitive audio interface, you are creating a direct physical bridge.
Right, all of that digital garbage from your graphics card marches right down the wire, infiltrating the clean ground of your audio equipment.
This creates what we call a ground loop.
And a ground loop alters the reference voltage of the entire audio system.
Which is bad because the deity relies on a perfectly flat ground reference of 0 volts to accurately translate the digital signal, right?
Exactly. If the ground is vibrating with noise from the computer, the deity's translation will be inherently flawed. You'll get audible hums or buzzing.
So how did Comonec fortify this USB gate in his 2013 design? He deployed a component called the ADUM4160.
This is a dedicated USB isolator.
And the best way to visualize this component is as a literal drawbridge and moat surrounding your audio fortress.
Electrically speaking, the ADUM4160 provides galvanic isolation.
Galvanic isolation. That's a term that gets thrown around a lot in high-end audio, but let's break down the actual physics of it. It means there's absolutely no direct, conductive, physical connection between the input side of the chip and the output side.
Right. Inside the microscopic packaging of the ADUM4160, the physical wire literally ends. There is a physical gap separated by a layer of polyamide insulation.
So wait, how does the data get across the gap if there's no physical wire?
Through magnetic induction. The chip takes the electrical USB signal, the digital ones and zeros, and runs it through a microscopic coil.
Okay.
This turns the electrical pulses into a fluctuating magnetic field. And this magnetic field easily passes right through the insulating gap.
Oh, wow.
Then on the other side of the gap, a second microscopic coil picks up that magnetic field and translates it back into a clean electrical signal.
That is amazing. So the dirty current from the computer reaches the edge of the moat, and the isolator effectively says, you stop here.
Yes.
The musical data gets tossed across the moat via the magnetic field, but the physical dirty electricity, the noisy ground from the motherboard, cannot cross the insulation.
The computer keeps it 30 ground, And the sound card gets to establish its own pristine, uncontaminated ground reference.
It is a profoundly elegant defense mechanism. And it's worth noting the historical context here, too. Komanek chose the ADUM 4160 because at the time the thesis was written, it was one of the very few USB isolators capable of full-speed operation that was actually readily available.
Right. It shows a designer working practically with the logistics of supply chains to solve a critical acoustic problem.
Exactly. So that secures the USB gate, but the sound card also features a second input gate, the Toslink optical connection.
And what's fascinating here is that the Toslink connection approaches the problem of electrical noise from an entirely different angle. It sidesteps the issue by abandoning electricity altogether during the transition phase.
Right, because Toslink uses fiber optics. Instead of sending voltage pulses down a copper wire, it sends the audio data using rapid pulses of red light down a plastic or glass fiber.
If you've ever unplugged an optical cable while the device is on, you've seen that distinctive red laser glow at the tip.
Yeah, it looks pretty sci-fi. And because the data is being carried by photons instead of electrons, it is physically impossible for electrical noise or ground loops to hitch a ride on the cable.
A fiber optic cable is immune to radio frequency interference. It provides absolute 100% galvanic isolation by its very physical nature.
So when those pulses of light reach the sound card, they hit an optical receiver module. In this project, it's the TORX-147.
Which acts as a photodiode, catching the photons and translating them back into a clean digital electrical signal on the safe side of the fortress walls.
So we have the magnetic drawbridge for the USB, and the POSIS-Link simply flies over the battlefield completely untouched. It's fantastic architecture. But, with multiple signals coming into the board, you need something to manage the traffic.
You can't just wire them all directly to the DAC. You need a brain to orchestrate the routing.
And in this design, the brain is a microcontroller, specifically an STM32 Cortex-M3 processor.
The STM32 is essentially the air traffic controller of the entire printed circuit board.
But just to be clear, it's not actually messing with the audio itself, right?
Correct. It is important to clarify that the STM32 is not a digital signal processor in this context. It is not touching, filtering, or altering the actual music data.
Okay, so what is it doing?
Its job is purely logistical and administrative. It monitors the user interface. When you press a button to switch from the USB input to the optical input, the STM32 registers that command.
And then it controls a multiplexer.
Yes, which you can think of as a complex rail yard switch. It physically reroutes the data path on the board.
And it also has to talk to all the other microchips. It sets the volume levels, configures the DSC, tells the resampler how to behave. It does this using specialized serial communication protocols called SPI and UART.
Right. Think of SPI, or Serial Peripheral Interface, as a dedicated high-speed telegraph line. The STM32 acts as the master commander, sending synchronized configuration data to the other chips, ensuring they are all operating in the correct modes.
Because without this microcontroller, a user would have to manually flip banks of tiny physical dip switches on the circuit board every time they wanted to change a setting.
Which would be a nightmare. The STM32 allows the system to present a sleek, modern user experience while managing massive complexity behind the scenes.
Okay, let's take a breath and survey our defenses. We have built a moat. We have our optical fiber bypassing ground loops entirely. We have our STM32 air traffic controller keeping the routing organized.
The voltage levels are clean.
We have successfully locked the dirty electrical noise out of the fortress. But I want to throw a wrench into this.
Okay, go for it.
Because getting a clean signal without electrical noise is only solving half the equation. What if the digital data itself, the actual ones and zeros coming from the computer, arrives at the wrong speed? Or what if the spacing between the data points is slightly irregular? If a song is stuttering or the tempo is microscopically shifting back and forth, having a noise-free ground line doesn't save the audio from sounding terrible.
That is a very valid concern. And it brings us to the second major enemy on the digital audio battlefield. We have defeated voltage noise, but now we must defeat timing errors.
And in audio engineering, this enemy is known as jitter.
Jitter is one of those buzzwords that gets thrown around endlessly in audiophile forums, often without a clear explanation of what it physically represents.
Yeah, I feel like people just use it to sound smart. So to truly understand jitter, we have to look at how digital audio functions over time. A digital audio file isn't just a static picture.
No, it is a continuous, relentless stream of data points that must be processed in real time. Standard CD quality audio is encoded at 44,100 samples per second.
That means the DAC chip has to read a digital value and translate it into an analog voltage exactly 44,100 times every single second.
And the interval between each sample must be rigidly, perfectly identical.
Let's visualize this. Imagine you are plotting dots on a piece of graph paper to draw a smooth, curving wave. The vertical y-axis represents the voltage, that's the data value of the ones and zeros.
And the horizontal x-axis represents time.
Right. If the grid lines on your x-axis are drawn perfectly evenly, you plot your dots, connect them, and you get a beautifully smooth sine wave.
But what happens if the grid lines on the time axis are slightly warped? What if one grid line is a millimeter too far to the left, and the next is a millimeter too far to the right?
Well, even if your data, the y-axis voltage value, is perfectly correct, plotting it on an uneven time grid physically deforms the shape of the wave.
Exactly. When you connect the dots, the wave is jagged and misshapen.
And in digital audio, the grid lines are dictated by a clock signal. If the clock signal telling the DAC when to process the next sample isn't perfectly metronomic, the resulting analog wave is physically distorted.
That unevenness in the clock is jitter. It is basically an electronic stutter.
And human ears are remarkably sensitive to this specific type of distortion, right?
Very sensitive. Jitter smears high frequencies, degrades the spatial imaging of a stereo mix, and just destroys the crystalline clarity that Comineck was trying to achieve with his negative 120 dB target.
The problem is that the internal clock inside a standard computer is atrocious for audio purposes.
It's dealing with a million other things.
Exactly. A PC motherboard is busy managing interrupts from the mouse, network traffic, background applications. The audio data stream coming down the USB cable is inevitably riddled with timing inconsistencies.
If the sound card relies on the computer's sloppy clock to time its conversion, the audio will be full of jitter.
So what's the fix? How did he solve it?
The solution is absolute independence. You must refuse to trust the computer's rhythm. You have to build your own perfect metronome inside the secure walls of the sound card.
And this is achieved through the clock generator circuit. In Comineck's design, he used a combination of a FOX924B precision crystal oscillator and a PLL11008 chip.
The FOX924B is a truly fascinating component. It contains a tiny physical piece of quartz crystal.
Like actual quartz.
Yes, actual quartz. Through the piezoelectric effect, when a voltage is applied to the quartz, it physically vibrates at a highly specific, immutable frequency.
And in this case, it vibrates at exactly 27 megahertz.
27 million times a second.
That is just mind-blowing, and it is incredibly stable. The source material notes its frequency tolerance is plus or minus 1.5 parts per million. That level of accuracy is staggering.
It acts as the local, incorruptible heartbeat for the entire sound card. Once this clock is running, the sound card completely ignores the sloppy timing attached to the data coming from the PC.
Okay, but this creates a new logistical problem, doesn't it? You now have two separate time domains. You have the dirty time domain of the data streaming in from the computer, and the clean time domain dictated by the 27 megahertz crystal on the sound card.
Yes, you do. And you cannot simply force the two together without massive data loss or skipping. You need a mediator.
And here's where it gets really interesting. That mediator is my favorite chip on this entire board.
Yeah.
The SRC4193 resampler. Specifically, it's an asynchronous sample rate converter.
It is the ultimate bridge between the chaotic outside world and the ordered environment of the DAC.
I picture the resampler as an obsessive-compulsive traffic cop. It catches the incoming audio data, which might be arriving with all that sloppy computer jitter, and temporarily holds it in a tiny digital buffer.
It completely strips away the original dirty timing.
Then it reorganizes the data and outputs it, locked perfectly in sync with the sound card's pristine 27 megahertz quartz metronome.
It decouples the input timing from the output timing entirely. The audio is safely transferred across the temporal divide without losing a single bit of information.
But the SRC4193 isn't just fixing the rhythm right, it is also fundamentally altering the format of the audio data itself. The thesis notes that the resampler takes standard 16-bit, 44.1 kilohertz audio, which is what most consumer music files are, and actively upsamples it to a high-resolution format of 24-bit, 192 kilohertz.
This is a point of frequent confusion in the audio world, and it really deserves careful explanation.
Yeah, I want to push back on this practice a bit, because audio companies use upsampling as a marketing gimmick all the time.
They absolutely do.
If the original CD or MP3 file only contains 16 bits of data per sample, you can't magically invent new musical information to fill a 24-bit container. It's like trying to run a low-resolution photo through a filter and suddenly read the license plate of a car in the background. The data simply isn't there.
Right.
So isn't upsampling just mathematically padding the file with empty zeros? Why go through the computational effort?
You are entirely correct that upsampling does not magically recreate lost musical detail. If a subtle echo wasn't captured in the original 16-bit recording, upsampling will not make it appear.
Exactly.
However, in low-level hardware design, upsampling is not done to add detail to the music. It is done to manage mathematical noise and make the physical analog filtering stage much easier to execute.
Okay, let's break down the physics of why that works. It basically comes down to digital headroom and quantization noise, right?
Exactly. When an analog acoustic wave is initially recorded and digitized in a studio, the computer has to round off the continuous, smooth curve of the wave to the nearest available digital step.
And in a 16-bit system, there are 65,536 available steps.
Right. And that rounding error, the microscopic difference between the true analog wave and the digital step it was forced onto, manifests as noise. It is called quantization noise.
It's basically the mathematical byproduct of turning something smooth into something staircase-shaped.
By using the SRC 4193 to upsample the signal to 24-bit and a 192 kilohertz sample rate, the system utilizes complex digital filters. These filters use interpolation algorithms to smooth out the staircase.
So they don't add new musical information, but they do take that quantization noise and push it higher up the frequency spectrum.
They shift the noise away from the frequencies that human ears were actually sensitive to. Through a process related to noise shaping, the mathematical artifacts of the digital conversion are pushed far beyond 20 kilohertz, deep into the ultrasonic range.
So the noise still exists, but you've swept it under a high-frequency rug where only, bats or dogs could possibly detect it.
Exact.
But there is another deeply practical reason for upsampling that involves the DTA chip itself, isn't there?
Yes, there is. High-end digital-to-analog converters like the PCM1792 used in this project are natively optimized by their designers to operate at peak performance when fed a high-resolution 24-bit 192 kilohertz signal.
Ah, I see.
If you feed them a standard 16-bit signal, the DAA has to engage its own internal, often inferior digital filters to process it.
So by utilizing a massive, dedicated external chip, like the SRC 4193, to handle the upsampling before the data ever reaches the DAA, you are allowing the DAQMI to operate in its most relaxed, default, optimal state.
Right. And furthermore, because you've pushed all that high-frequency digital noise into the ultrasonic range, the physical analog low-pass filter that sits after the DAA doesn't have to be a steep, aggressive brick wall filter.
It can be a gentle, smooth filter.
Which introduces far fewer phase distortions into the audible music. It is a textbook example of holistic system design. Every component is chosen not just for its individual specs, but for how it makes the job of the next component in the chain easier.
That makes total sense. So let's take stock of the signal path so far. We have built the galvanic moat to block dirty ground currents.
Yep.
We have used a quartz crystal to eradicate jitter and establish a perfect rhythm. We have deployed the resampler to reorganize the data, push the mathematical noise into the ultrasonic ether, and spoon-feed the D its ideal format.
The digital signal is now as immaculate and perfectly timed as it is ever going to be.
And now we cross the Rubicon. We move from the realm of digital mathematics into physical, analog reality. We arrive at the heart of the system, the digital-to-analog converter, the PCM1792.
This chip really is the crown jewel of Commonex board. The source material notes its pedigree. It is a component heavily utilized in professional exorbitant audiophile gear.
Because it boasts a 24-bit resolution, a 192 kilohertz maximum sampling rate, and a staggering dynamic range of 127 decibels.
The DA is the literal translator. It reads the cold binary logic of ones and zeros and converts them into the fluctuating analog electrical wave that will eventually push the magnets inside your headphones, moving the air that hits your eardrums.
It is the exact moment the abstract code becomes living sound. But there is a very specific, deeply technical engineering choice in how the PCM1792 operates that caught my attention.
What's that?
Well, when it performs this translation, it does not output a voltage signal. It outputs an analog current signal.
Yes, the PCM1792 features a current steering architecture. It outputs a fluctuating electrical current rather than a fluctuating voltage.
But why design it that way? Headphones and amplifiers need voltage to push the speaker drivers. If the D chip outputs current, isn't that just adding an extra step? The hardware designer is forced to build an entirely separate, complex circuit, a current-to-voltage converter, just to make the signal usable.
It does seem counterintuitive at first.
Why wouldn't Texas Instruments just integrate the voltage converter directly inside the D chip and save the designer the headache?
Well, many cheaper consumer-grade GD chips do exactly that. They integrate the IV conversion on the silicon die itself to save space and cost. But remember the ultimate objective of this thesis.
Uncompromised clarity.
Right, uncompromised clarity, maximum control, and a negative 120 dB noise floor. The pursuit of absolute perfection requires separating these tasks.
Let's examine the physical environment inside the silicon die of a DIC chip for a second. It is microscopic, and it is incredibly busy.
Extremely busy. You have digital logic gates switching at millions of times a second right next to delicate analog conversion pathways.
And this proximity creates parasitic capacitance and severe thermal gradients. The silicon gets hot, and that heat creates thermal noise.
Converting the delicate output current into a robust, usable voltage swing is an incredibly sensitive analog process. If you force that conversion to happen inside the cramped, noisy, thermally volatile environment of the D-ticket itself, the signal will inevitably pick up interference.
I like to compare this to photography. The DC's job is to capture the raw light and produce a perfect, delicate chemical film negative. The current output is that pristine negative.
That's a great analogy.
If you try to develop that negative into a photograph while cramped inside a tiny, hot, and noisy photo booth inside the camera itself, you are going to get a muddy, compromised print.
That is exactly it. High-end chips, like the PCM1792, are designed with a specific philosophy. We will perform the immensely complex digital-to-analog translation perfectly, and we will stop there. We will hand you the raw current, and we will leave the critical task of voltage conversion up to you, the hardware designer, to handle in a superior external environment.
It's all about ultimate control. By outputting current, Commonic was able to take that pristine film negative and develop it in a massive, dedicated external darkroom. He designed his own ultra-high-quality external current-to-voltage converter using discrete operational amplifiers.
Specifically, he utilized 4 OPA-134 op-amps from Texas Instruments. These are physically larger, vastly superior analog components compared to anything that could be crammed onto a D-shy.
And because they sit externally on the circuit board, they have their own clean power delivery, they can dissipate heat effectively, and they operate far away from the high-frequency switching noise of the digital section.
They take that raw current and meticulously translate it into a beautiful, clean, massive voltage swing without adding distortion.
And finally, that pristine voltage signal is passed to the headphone amplifier stage. The thesis details the use of the TPA612AA2.
The headphone amplifier's role is crucial here. The OPA-134 provides the correct voltage shape, but it doesn't have the brute physical strength to push the heavy magnets and speaker cones inside a pair of audiophile headphones.
The TPA612A2 provides the muscle, the high current drive capability, necessary to physically force the headphone drivers to move in exact accordance with the voltage wave, without sagging or altering the shape of the wave under load.
So if we look at the schematic on a computer screen in 2013, we have a theoretical masterpiece. The USB isolator, the optical bypass, the quartz metronome, the resampler, the premium current output DAC, the external op-amp darkroom, and the high current amplifier.
On paper, it is an impenetrable fortress of audio fidelity. But hardware design is a brutal discipline because a schematic is merely an idea.
It's just theory.
Right. Dragging a theoretical circuit off the computer screen and manifesting it in physical reality, in the literal metal, fiberglass, and copper of a printed circuit board, is where the real world fights back.
The physics of electromagnetic fields, thermal dynamics, and parasitic trace capacitance come into play. This brings us to the physical design phase of the thesis, which is where Commonec's engineering rigor is truly tested.
The transition from schematic to physical PCB, printed circuit board, is arguably where the most critical decisions are made regarding noise rejection. The source details that Commonic designed a 4-layer PCB meticulously routed down to the millimeter.
Let's explain why a 4-layer board is so vital here. A cheap consumer device might use a simple 2-layer board. 1 layer of fiberglass with copper wires routed on the top and copper wires routed on the bottom.
But a 4-layer board is a significant step up in manufacturing complexity and cost. What are those extra 2 layers hiding inside the fiberglass actually doing?
They act as dedicated highways and electromagnetic shields. In a 4-layer stack-up designed for low noise, The top and bottom layers are typically utilized for routing the signal traces, the physical paths the audio and digital data travel along.
Okay, so the outside is for the data.
Right, but the two hidden internal layers are solid, continuous planes of copper. One is usually dedicated entirely to power distribution, and the other is dedicated entirely to ground.
Having a solid copper power plane means that instead of trying to run a thin, fragile wire across the board to provide power to a hungry chip, the chip simply drops a microscopic via straight down into a massive sheet of copper to draw whatever current it needs instantly, with minimal resistance.
It provides incredibly stable power delivery. But even more importantly, those solid copper planes act as physical electromagnetic shields. They absorb stray radio frequencies and prevent the magnetic fields generated by the digital traces from inducing noise into the delicate analog traces.
And the routing of the ground plane itself is an art form. The thesis mentions a brilliant detail regarding how the board handles ground returns.
The star grounding concept.
Yes, the physical board is visually split. The noisy digital components are grouped on one side, and the delicate analog components are grouped on the other. But the ground plane beneath them is also split.
The digital ground and the analog ground are carefully kept separate.
And they only physically connect at one single specific microscopic point on the entire board, directly beneath the PCM1792 DIA chip.
This technique is designed to absolutely prevent those ground loops we discussed earlier. Electric current always seeks the path of least resistance back to its source.
So if you have a unified ground plane, the noisy return currents from the digital logic chips might wander through the copper on the analog side of the board,
which would introduce microscopic voltage ripples into the audio path. By splitting the planes and tying them together at a single point, you physically force the dirty digital currents to stay on their side of the board. It is literal physical crowd control for electrons.
And all of this brilliant four-layer copper architecture was designed to slide perfectly into a Hammond aluminum enclosure. Now, Hammond cases have a wonderful, rugged, industrial aesthetic, but I know the choice wasn't just about making the device look professional on a desk.
The aluminum enclosure serves a vital physical function.
Yeah.
It acts as a Faraday cage.
A Faraday cage is a continuous enclosure of conductive material. Because aluminum conducts electricity, any external electromagnetic fields, like radio waves, Wi-Fi signals from your router, the massive electromagnetic field thrown off by your computer monitor,
They hit the aluminum case and are dispersed across the surface.
they cannot penetrate the metal to induce noise in the circuits inside. It traps the clean audio environment inside and completely locks out the ambient electromagnetic chaos of the room.
So with the fortress fully constructed and shielded in copper and aluminum, Komanek arrived at the grand experiment of the thesis.
Because he didn't just want to build a working sound card, right? His academic goal was to test optimization strategies.
Yes. He wanted to scientifically prove whether the exorbitant practices of the high-end audiophile industry were actually necessary, provided the core architecture of the board was sufficiently robust.
And the results of his power supply tests are arguably the most provocative part of the entire paper. If you look at high-end, multi-thousand-dollar audio gear, the manufacturers will always brag about their power supplies.
They love talking about their massive, separate toroidal transformers.
Right. One heavy iron transformer dedicated purely to powering the digital section and a completely separate one dedicated to the analog section. It looks impressive, it weighs a ton, and it drives the cost of the unit through the roof.
It is a deeply entrenched belief in audiophile circles that absolute physical separation of power at the transformer level is a strict requirement for ultimate sonic clarity.
But Komanek decided to test this dogma mathematically. He powered his sound card using a dual transformer setup, isolating the analog and digital lines, and measured the noise floor. Then he stripped one transformer away and powered the entire board, digital and analog, from a single transformer and measured it again.
And the data was shocking.
Did the single transformer collapse the pristine noise floor?
The difference was almost mathematically non-existent. The dual transformer setup increased the signal-to-noise ratio by a mere 1 decibel.
1 single decibel, which is completely biologically imperceptible to the human ear.
He proved that demanding 2 massive transformers for this specific smartly designed architecture was practically meaningless.
But he didn't stop there. He took aim at the voltage regulators next.
Voltage regulators are the components that take the raw power from the transformer and smooth it out into a perfectly flat DC voltage before it enters the sensitive microchips.
For the analog power supply, he initially utilized ultra-low noise, premium regulators from Texas Instruments, the TPS-7A47 and the TPS-7A3301. These are state-of-the-art parts with a noise floor measured in microvolts.
But to test his optimization theory, he swapped them out.
For the headphone amplifier section, he ripped out the expensive chips and soldered in incredibly cheap, standard, run-of-the-mill regulators, the LM317 and LM337.
To put this in perspective, these standard regulators cost roughly 3 Polish zloty combined. That is less than a single US dollar.
The expectation would be that injecting cheap regulators into the power path would ruin the signal.
The drop of ink should have poisoned the water, basically.
But the result, the noise parameters of the audio output remained almost entirely identical. The audio wasn't ruined.
Which begs the question, how is that physically possible? If cheap regulators inherently generate more power supply noise, why didn't that noise manifest in the audio output?
It comes down to the architecture of the components further down the line, specifically a concept called PSRR, power supply rejection ratio.
Exactly. The OPA 134 op amps used in the current-to-voltage conversion stage are deployed in a differential configuration. This means they process the audio signal by looking at the difference between a positive signal line and a negative inverted signal line.
And here is the genius of differential signaling. If the cheap LM317 voltage regulator injects a spike of power supply noise into the system, that noise spike travels down both the positive and the negative signal lines equally.
It is what we call common mode noise.
When the op-amp calculates the difference between the two lines to output the audio, the noise spike on the positive line mathematically subtracts the exact same noise spike on the negative line.
The noise literally cancels itself out. The op-amp rejects the power supply noise through sheer mathematics.
The circuit design was so fundamentally robust and the PSRR was so high that the Fortress simply didn't need the platinum walls of the ultra-expensive TPS regulators.
The cheap $1 regulators were perfectly sufficient because the architecture naturally purged their flaws.
It is a massive vindication for Komanek as a designer. It proves that intelligent engineering beats blindly throwing money at a problem every single time.
It is a triumph of applied science over audiophile mysticism. However, hardware design has a brutal way of keeping engineers humble.
Doesn't it just?
Despite its successes with the power supply optimization, the physical testing phase revealed a critical error. This brings us to the famous capacitor mistake.
This is the ultimate plot twist of the thesis. After all this brilliant engineering, all this success proving that expensive transformers are redundant, Komanek runs a final frequency response test.
The goal of this test is to ensure the sound card is outputting all audible frequencies equally.
From 20 hertz, the lowest rumbling bass, all the way up to 20 kilohertz, the highest shimmering treble. On a graph, a perfect frequency response looks like a perfectly flat horizontal line.
A flat frequency response is the baseline requirement for high-fidelity audio. The device must not artificially boost or cut any frequencies.
But when he ran the sweep, the line wasn't flat. He observed a weird, highly noticeable voltage drop occurring across the high end of the audible band, specifically a drop of about 0.7 to 0.8 dBu.
The treble frequencies were literally being strangled by the circuit.
In an analog circuit targeting Argidich 120 dB of distortion, an IDICH 0.8 dB dew drop in the frequency response is a catastrophic failure.
And this is where the forensic detective work of hardware debugging kicks in. He had to trace the schematic to find out why the physics of the board were failing.
And the culprit wasn't a faulty multi-dollar Texas Instruments chip. It came down to one single, tiny, seemingly insignificant component.
During the assembly phase, when Komanek was ordering parts for the current-to-voltage converter, he required a very specific capacitor, a 2.7 nanofarad capacitor.
But that specific value wasn't available from his supplier at the time, so he substituted it with a 3.3 nanofarad capacitor.
It is incredibly common in basic electronics to substitute a slightly larger capacitor, thinking, it's close enough, it will do the job.
But in the context of an active analog filter, close enough alters the fundamental math of the circuit. Let's explain the physics here quickly.
Okay.
A capacitor paired with a resistor creates an RC circuit, which functions as a low-pass filter. It allows low frequencies to pass through, but blocks high frequencies above a certain point, known as the cutoff frequency.
The math dictating that cutoff frequency is absolute. Frequency equals 1 over 2 times pi times resistance times capacitance.
By taking that formula and inadvertently increasing the capacitance from 2.7 nanofarads to 3.3 nanofarads, he mathematically dragged the cutoff frequency down.
He dragged it down so far that the filter started aggressively shaving off the high end of the actual audible music spectrum.
It perfectly illustrates our metaphor from the beginning of the discussion, the drop of ink.
Exactly.
One slightly incorrect tiny capacitor, a passive component that costs pennies, completely altered the mathematical reality of this beautifully designed complex sound card.
It is a stark reminder of the fragility of analog design. But because Kamenek approached the project with immense rigor, he isolated the variable.
He ran a test with those specific capacitors removed from the board entirely, and the frequency drop vanished instantly.
The line was flat again. He recalculated the RC filter math, ran simulations in software to confirm, and eventually ordered and installed 2.2 nanofarad capacitors instead.
The math was corrected, the water was clear again, the sound card functioned flawlessly.
It is a beautiful illustration of the reality of hardware development. It is rarely a straight line. It is a relentless cycle of theoretical design, physical manifestation, rigorous testing, inevitable failure, forensic analysis, and correction.
And understanding that cycle makes you appreciate the final product so much more. This has been such an incredible journey through the microscopic world of audio electronics. So to synthesize all of this, the next time you sit at your desk, plug your headphones into that little metal box and hit play on your favorite track. I want you to pause for a second.
I want you to visualize the microscopic battles happening inside that enclosure.
Think of the invisible wars being fought every single millisecond. Think about the galvanic moats and magnetic drawbridges physically blocking the dirty power of your computer from invading the circuit.
Think about the 27 megahertz quartz crystal violently vibrating to fix the digital stutters and maintain a perfect metronomic heartbeat.
Think about the resampler acting as the ultimate obsessive traffic cop, reorganizing the chaotic data and pushing mathematical noise into the ultrasonic ether.
And think about that delicate, profound magic trick inside the DSC, translating cold binary code into a raw current, which is then developed into the living, breathing analog voltage that physically hits your ears.
It demands a deep, profound respect for low-level hardware engineers. They are the unsung heroes constructing the physical architecture of our daily soundtrack.
They absolutely are. The level of passion required to navigate these physical laws is inspiring. And if we zoom out and view this 2013 project in the context of where we are today, it leaves us with a truly fascinating, almost philosophical question to ponder.
Oh, I like where this is going.
We just analyzed a university student who, over a decade ago, utilized free sample chips and brilliant architectural strategies to build a device that goes toe-to-toe with modern, highly expensive audiophile equipment. It successfully conquered the physical limits of electronic noise.
Right.
It raises a provocative thought. In the realm of audio playback, have we reached peak hardware?
I see. If a well-designed circuit from 2013 can achieve a noise floor of necking 120 decibels, which is vastly cleaner than anything a human ear could ever hope to distinguish, is the quest for perfect sound no longer about the metal and the silicon?
Are the machines already vastly superior to our own biology? Have we reached a plateau where the only remaining limiting factor in audio fidelity isn't the resolution of the DAA, or the stability of the clock, or the slew rate of the amplifier, but is entirely dependent on the physical biological limits of our own human eardrums and how our auditory cortex processes sound?
We spend thousands of dollars trying to upgrade the hardware on our desks, when the actual bottleneck might be the hardware inside our own heads. That is a heavy thought to mull over. The next time you close your eyes, put on your headphones and just listen. Ask yourself, are you hearing the limits of the engineering, or are you finally just hearing the limits of yourself?
That's a great question.
I am certainly going to look at the gear on my desk a lot differently from now on. We have covered incredible ground today, from thermal noise to Faraday cages, and I hope it gives everyone listening a new appreciation for the science of sound. We'll leave it there for today's deep dive. Until next time.